negative, that can be anywhere where the the derivative changes from negative to positive, and it just depends what specific you're going
interval you're looking at. Yep. Okay.
So possibly you could have a whole bunch of ellipses.
Yep. Okay, h of x has an absolute minimum. Okay, key phrase, of something at x equals where? So what is the height of that minimum? Yep. So of negative 26 at x equals 3. Okay, key phrases, you need to say that. And you also have to explain how you know this. How do we know this? Because h prime of x changes what? From negative to positive, because it's decreasing and then it increases. Also, to prove it's the absolute and not just a local, you have to show we have another minimum. So we'll say and because h of 0 equals 0 and h of 3 equals negative, not 36, 26. Is 0 lower than negative 26? No. So since this one is the lower one, it has to be the absolute minimum. Oops. Okay. Local. Local maximum. Do we have a local maximum? I think there's another local maximum. Yeah, this is an endpoint, so it's higher than that one. Okay, so we have h of x has a local maximum of, what's the height of that point? 38 at x equals negative 1. So h of x has a local maximum of 38 at x equals negative 1. We know this because what? Does it change from negative to positive? But we know that on one side it is decreasing from then on, right? Okay. Because h decreases to the right of the endpoint. Yeah? It's not the highest, actually. This arrow goes on forever. Okay, so on the absolute, because of that arrow, is there an absolute? No, because it goes on forever. So h of x does not have an absolute maximum because the limit as x goes to infinity of h of x doesn't end, right? It goes to infinity. Okay. As we go to the right, the graph goes up and up and up forever, so it goes to infinity. Okay. So, candidates for absolute maximums, fill in the blank maximum. For absolute maximums are where the f prime changes from, yeah, because you have to be increasing and then you have to be decreasing to get a maximum, right? So, positive to negative. And it could be at the endpoints. Keep those endpoints in mind, because sometimes they sneak up on you. Candidates for absolute minimum, and remember this is absolute, not just relative, this is absolute, are where f prime changes from negative to positive, and it could be the endpoints. So keep those endpoints in mind. Okay, flip over. Find extreme values. Be sure to complete the 5-step process which we worked on last time. First step is to do what? Find the domain. Excellent. What type of function is this? Cubic. We know cubic functions look something like this, right? So the domain is all real numbers, or you can say negative infinity and positive infinity. Okay? What's the second step? Find the dy dx. Okay. Ethan, what would dy dx be? Great. Yep. Okay. Next step. Critical points. And restricted values, right? Okay. Critical points. We set the numerator or the function equal to 0. When we do that, we have a quadratic. So how do we find critical points of a quadratic? Factor. Two numbers that multiply to negative 15 but add to 2. 5 and 3, but which one has to be negative? Then 3 has to be negative. So remember, these are factors, they're not the solutions. The solutions, you use the 0 property, and you set them equal to 0 individually. So we have our critical points at x equals negative 5 and x equals, it needs to be positive 3, not negative 3. Restricted values happens when we have any points that are undefined, such as denominators being 0. Do we have any issue with that? So that's none. Okay, now we do a sign chart. You have, where's your number 2? Is it below or to the right? Okay, I'm going to come over here. Sign chart, and you need to be labeling this. This is dy dx, or you can say f prime. You need to label. And put your critical points on, negative 5 and 3. It's now become a quadratic. You need to know what quadratic graphs look like. A quadratic, this one's a positive. What do positive quadratics look like? Yeah, it goes like this and like this. And at some point it's going to cross the axis. So it starts positive, then it crosses and gets negative, and then it starts increasing again and gets positive. So part E, the answer for us, we're not doing, you can do, we know the intervals of this is increasing, this will be decreasing, and this is increasing. For our purposes today, we're looking at the relatives mins and maxes. So, do we have any mins and maxes? Yeah. Where? X equals negative 5. If we're changing from increasing to decreasing, it is a Increasing to decreasing, it would be a maximum. And this one is changing from decreasing to increasing, so it would be a minimum. Now the question is it a local or is it an absolute? Why would it have to be a local? Because the original function goes on forever, right? Up and down. So it doesn't have an absolute max or an absolute min because it goes on forever. So these would be local. Another word for local, by the way, is relative. So f of x has a local, or you can say relative, be used to both of those, max of something, we don't know that yet, at x equals negative 5. How can we find the of? Plug in negative 5 into what? The position, the original. So you guys can plug that in really quick. I'll just tell you. We're running out of time. It's a decimal. 59.333. 4 decimal places. Because we know this because f prime of x changes from what to what? Positive to negative. Okay, and we have a local f of x has a local min of something at x equals 3. How would we find the of? Plug in x equals 3 into what function? The original function. So it'll end up being negative 26, okay? Because f prime of x changes from negative to positive. Yeah? The derivative is a parabola, but this is actually finding things about the original function that goes up forever and down forever. Because you want to find, because there's these bumps in here. You want to find what's the height of that bump and the height of this bump of the original. Hey, let's do another one. I'm going to do number 3, actually. Go to your number 3. Okay? This function, the domain. So all real numbers. One, and there's another one. Negative 1. We have a restricted value because the denominator can't be 0. So x squared minus 1 equaling 0. If we add 1, x squared equals 1. When you take the square root, x can't be plus and minus 1. Those are restricted values. So domain would then be negative infinity to negative 1 union negative 1 to positive 1 union 1 to infinity. What's a simpler way to write that?
All real numbers except
X equals plus or minus 1. Yep. You can say all reals, can't spell, except x can't equal plus or minus 1. That's actually about the same length, isn't it?
But is there a symbol for all real numbers?
Yeah, you can say,
And then but x cannot equal.
yeah, you could say the set of all real numbers such that x does not equal plus or minus 1. There's lots of ways to write domain. There's like 4 different methods to write domains and ranges. Okay, dy dx. Ho d high minus high d ho over ho ho. Sorry I used the hos instead of low, but it's also low d high minus high d low over low low. I just think ho ho is funnier. Okay, so ho x squared minus 1 d high. What's the derivative of the high? 0. So that's going to cancel. minus high d low. What's the derivative of the low? 2x over the denominator squared. So we have negative 2x. Notice carrying down my equal sign, writing equivalent statements. I hope you're practicing carrying it down, writing equivalent statements. X squared minus 1 squared. Okay? Okay, critical points. Critical points is setting the function equal to 0, which is really just setting the numerator equal to 0. Because you can you can times out the denominator. Okay, so this is numerator equal to 0 versus the restricted value is denominator equal to 0. Okay? We set the numerator equal to 0. What critical point do we get? 0. Divide out negative 2. We have a critical point at x equals 0. And restricted values for the denominator can't be undefined. Well, we can't have a 0 because it makes the function undefined. If I square root both sides, I get 0 equals x squared minus 1. What restricted value do we end up getting? Good, there are 2. You take the square root, and we get x equals plus and minus 1. Okay, so those become our points of interest. Next step, y dx or f prime of x, you should be labeling. We have negative 1, 0, positive 1. Okay, dy dx is a little complicated to see what's going on. I think the original function is actually a little easier to see what's going on. What happens when you plug in any x into an x squared? It turns positive. Okay, so if that is smaller than negative 1, like say negative 2, how do rational functions look? Almost always. Here's negative 1, here's positive 1. So it'll be positive and positive, but if we plug in, say, 0, 1 divided by negative 1 is negative 1. So we'll have a little bit of decreasing in there. So it goes positive, negative, oops. So this is off of f prime. So this one is increasing, increasing, decreasing, decreasing. So try them on your homework. We'll answer questions on this next time. 5-2 is due, though, next time. Okay? I'll be here after school. I would maybe not do your next derivative test today after school. I would study a little bit. Maybe you. I don't know. You might be able. You just had that one little error. You're close, though. Okay. Thank you.
I can do the day after school anyway, but I would do this many times. You know, the time I tell like go slow, don't make any mistakes, and then go slow about.
Yeah. Yesterday, at Split, we were doing this really intense thing, which I don't